I can translate. But I would like to see how you teach, for example, Bell inequalities and contextuality, you know, the Cohen-Specker theorem, using these kind of pictures.
Yeah, so
Intuition.
the whole of part 2 of the book is Bell's theorem. You guys can still see my screen.
Yeah.
Yeah. Okay. For some reason, I can't bring it to the front. What's going on? Oh yeah. Sorry. It's more just that I maximize so I could see you lot and now I'm covering over. Yeah. So the whole of part 2 of the book is Bell's theorem, and Bell's theorem is a little bit subtle because, I mean, it's not just that the theorem's subtle, but it's normally phrased in terms of an inequality that you then violate statistically by like repeating an experiment. And I really don't like, you know, students, me, undergrad students, everyone's bad at statistics and probability. And so telling people like, oh, you know, this thing is amazing because now you go and measure and you see that this fraction of these types of observations is made instead of what you were expecting, which was that fraction of these observations. It's just like, it's just not as compelling a story. So in the book, I used a version of Bell's theorem or of quantum non-locality that's due to Harding. And it's more a logical impossibility type version of Bell's theorem. It's not as experimentally robust, but it's like you can work through and logically see that what happens is impossible if the theory is local in the sense of, you know, in the sense of Bell locality. I then added on the web page some notes here at the end of this FAQ. I had originally started trying to teach Bell's theorem like via the CHSH inequality. So you can go through and read this. And this was sort of an early draft of where I was going to try and do CHSH. And then I realized like, I just don't want to teach it via statistics, but you know, there's a whole setup here that will run through it as basically as a game again. I set up a game where you have people who claim they're psychic and you're skeptical that they're psychic. And then of course the psychics are psychic because they can cheat by using quantum non-locality as opposed to you know, what you're expecting, which is that the world is local. Anyway, so yeah, you can certainly teach Bell's theorem. Cohen-Specker theorem is not in the book. And there's many things that are not in the book, but because the formalism in the book is universal, you can teach anything. I mean, I think it would be painful to teach some things, like, but you can teach anything, teleportation. You can teach a Cohen-Specker theorem, and there's sort of a funny thing in the book, part 3 of the book. There's a measurement in part 3 of the book that is exactly equivalent to kind of a version of the Perez moment square, which is one of the classic versions of contextuality. So you can teach that as well. Most of these things, the hard thing is setting up a narrative that is not jargony so that the students can appreciate why it's actually interesting or mysterious or whatever. We are so used as quantum physicists to just like, you know, mangling all this stuff together, and the separations are clear to us, that when I sit down and try and think, okay, like, you know, try and come at it from someone who doesn't know any of this stuff, keeping that separation right, and then showing the calculations get a bit messy. But normally, if you're going to go that far into a course, I would imagine you'd have them program some Python or something to do the calculations for them or things like that. But yeah, getting the right story is hard.
So, but I mean, here, I mean, I didn't read this, but I mean, how much different is from, you know, the quantum mystery story of David Mermin? Because that's
I mean, it's similar, but his is still this kind of statistical thing. He did a statistical version. I just think, you know, especially for very young students, you're probably better not doing something that you know, that's sort of probabilistic in that sense. But yeah, you know, Bell's theorem is a passion of mine. I mean, that's why I'm still in physics in some sense. So finding many, many different ways of teaching it, I think is very good for the community, because at some point the penny will drop with everyone, and you know, and that will amaze them. And certainly would not claim that this is the only or the best way of teaching it, for sure.
Thanks.
Okay, any other questions?
Quick question for those of us who grew up on Boolean logic and group theory and things of that nature. Is Bell's theorem sort of an analogy of what we would know and love as Boolean algebra extended to this particular space?
Bell's theorem is really a theorem about the actual physical world and correlations in the physical world. So correlations in the sense of, you know, we have two separated systems. Maybe one is here and one is on Alpha Centauri. And we can make observations which are incompatible with a classical probability theory, i.e., they cannot have arisen by some joint distribution over some underlying systems, even if you don't know what those systems are. So the standard way of interpreting that, or at least talking about, is that, well, what I did here was not independent of what happened on Alpha Centauri in some non-trivial way. And then people argue about in what way was it not independent. It could have been that what I chose to do was not actually independent of what you were doing on Alpha Centauri, that we do not have the ability to make free random choices of measurements to do on the system. Or it could have been that there really is a superluminal signal from when I do my measurement to your system on Alpha Centauri, or et cetera, et cetera, et cetera. So Bell's theorem is really it's a theorem about observed statistical data in the world that should not be possible under, let's say, a normal, natural, classical, Boolean, logical view of the world. The calculation, you know, of examples of Bell's theorem can be done in this formalism. And as I said, this formalism is just a twist. Like it's like Boolean logic plus this one extra twist, this Pete box. But it turns out that Pete box is incredibly powerful. And so I shouldn't, you know, it gives us the power of quantum computing, and it gives us the ways to compute these sort of Bell theorem results and so on. But yeah, it's not like Boolean logic plus just a little bit. It's really like Boolean logic just blowing wide open, I guess.
It's really a composability theorem then, in the sense that it...
Composability theorem.
Yeah. Okay, got it. Thank you.
Sure.
So any other questions? If you have questions, you can just pick them up, or you can write in the chat.
I have a question about technology, not so much teaching. So I don't know if it's relevant to this.
Sure.
I've seen that you made the point that the only way for a useful quantum computer to be implemented is through photonics rather than any other technology. What about silicon, for example? I realize that superconducting materials is problematic and going to zero, close to 0 Kelvin, but what about demonstrations of semiconductor-based quantum computing platforms operating up at 4 Kelvin?
Yeah, like so, you know, it's definitely my personal bias is that no one has really laid out an architecture to building a machine of 1 million qubits other than photonics. And I only know that because I've laid it out over multiple years with 30 odd people simulating this thing from one end to the other. So it's definitely a personal bias. There's many, many other ways of building qubits. Photons are very different. They don't, you know, they don't decohere in the way that other qubits do. But, you know, it's not. So the nice thing about this kind of formalism, as I sort of intimated at the beginning with the black and the white, is there's many different quantum degrees of freedom that you could use. You could use the positions of the particles or the spins in silicon or nuclear spins, or you could use, you know, many other degrees of freedom. And then the hard thing is essentially, how do you prevent the world from making that observation that destroys that mist, the thing that sort of wrecked when I stacked 2 Pete boxes? How do you do that? And with photons, that part is actually very easy. Making the Pete boxes very easy, and preventing them from being observed is pretty easy. The hard thing with the photons is almost the opposite thing. It's like build the things like the C-swap. And so we have to go through completely different routes to do the classical things because the photons don't interact. So it's sort of the power of photons is they don't interact, so you can kind of isolate them incredibly well. But the thing that makes it difficult is that they don't interact. So you have to build your quantum computer in slightly different ways. But yeah, like there's many other reasons why I personally like the photonic approach. The gates are fast, the constraints are, the quantum part is already done. The scalability is the same. We use the same manufacturers as build your laptops and cell phones. We're limited only by like the speed of classical electronics. There's nothing to do with the fundamental Hamiltonians of the qubits that limits the speeds of the gates. And just there's an ongoing list that at some point, I'm sure the quantum computers in 100 years will be photonic because they're not limited in the way that other systems are. Whether or not the first quantum computers are photonic is, the gamble that we're taking.
And back to teaching. So you speak of teaching these principles and the math and all that to young students. Do you also attempt to teach these implementation aspects? That really requires some deep background.
Yeah, but the same would be true of classical computing. You can get students to the point where they can program and that they can appreciate the connection between, writing programs and logical constructs in their brain without them ever understanding how a classical computer really works. And I sort of feel like that is the step I would like to see augmented with the equivalent quantum thing. But yeah, for the rest of that stuff, you typically do need to at least have a full, 3 or 4 years of physics or math, computer science.
Right. Well, thank you. It's really wonderful that you encourage young people into this field and you teach the way you do. I wish I were a student of yours.
It's never too late to be a student.
Thank you.
Pleasure.
So I saw a few other things in the chat. Any other questions?
I have a question. So let me up here. So do you cover measurement-based quantum? And if not, how would you suggest teaching it?
In the book? No, I don't get anywhere near it. But I've taught it quite a few times at summer schools. And, the way I go about it, there's different ways you can go about it. The way I go about it is via teleportation. So you can certainly teach teleport, and I have taught teleportation using the formalism in the book. And then measurement-based quantum computation is basically, you can teach it as sequential teleportations. That's one way of doing it. But yeah, I guess what I should say about this whole thing is I am not advocating that we replace, undergrad level quantum mechanics by the formalism in this book. Because as you see, it's painful to sit and draw all these figures and all this kind of stuff. And plus you do lose powerful features of linear algebra, right? What I've really done there is I'm using string rewriting rules instead of using matrices and vectors. But the string rewriting rules don't capture geometrical concepts like rigid rotations and things that are important if you want to do efficient quantum analysis or think up good things. So I'm not advocating that. What I'm saying is I think that we can get students to like a quantitative understanding of a lot of quantum mechanics before they have to learn all of the rest of that math. And then my hope would be that there is a subset, like some sort of hybrid between all of the math of advanced quantum mechanics and this thing that I've been laying out, which one day will get us to the point where people will be able to work as a quantum mechanic, like work as, in the quantum workforce without having to go through the sort of an advanced quantum degree, much like today, the vast majority of software engineers did not do a CS degree at MIT or something, right? Like that's just not what they did. And so if we want to head towards that, getting students to the point where like the quantum stuff is not quite as mysterious, but that they have a quantitative grasp of it I think would be super, super fruitful for the industry. Of course, as I said at the start, like, that's a decision for policymakers and ultimately teachers, and not me.
Thank you.
Sure.
So we're spread all over the world, but and that's why we should wait to make sure that everybody has a chance to answer the question, to ask the question. But are there any other questions that we can address now?
It was interesting experience doing the talk from quarantine. But yeah.
I think that we set this up because we didn't know whether you would be in California or in the UK, and it turns out that you're in neither.
Neither.
So if there are no other questions, then I just want to extend my thanks to the speaker who was so gracious in accepting this call, and to everybody who came here, and just end the call. Thank you so much.
Thanks a lot.
Thank you. It was a great talk. Thank you.
Bye-bye.